In quantum mechanics, the canonical commutation relation is the fundamental relationship between canonical conjugate quantities, quantities which are related by definition such that one is the Fourier transform of the other. Think about the position and the momentum. Now, the commutator brackets are another algebra and needs to work within its definitions. And in this video, we will discuss some of the identities. Other things that you may have seen from classical mechanics would be the Poisson bracket, or if you like abstract algebra and Lie algebras, you'll see some of them in there. But in part A, we have two properties. Here we see that the commutator of a sum is the sum of the commutators. This is known as the linearity property. In the second property, we have a product on the left-hand side. So the commutator of a product is equal to the product sum of a couple commutators, which lets us know that this is a distributive law. So a distributive property, we've seen those before too. Just be careful due to the order and the fact that these are operators. Part B, we want to show that the commutator of x to the n and the momentum operator is equal to I h bar in x to the n minus 1. This kind of feels natural with the derivative that the momentum has. And then the C looks like we're just trying to generalize what we did in B for any function f of x that admits a Taylor series. To me, that lets us know that we're, convergent to a necessary bound, but also that we have powers. We're just power rules, so. And then part D, we want to show that for the simple harmonic oscillator, the commutator of the Hermitian, the Hamiltonian with the raising lowering operators, again, be careful of the plus minus nature, is equal to plus or minus h bar omega with the operator plus minus. This kind of feels natural from what we saw back in chapter 2, but nonetheless, let's go ahead and prove these statements. Alright, so in part A then, we just have to be aware of that this notation is for commutator brackets, not just grouping. What is the commutator bracket? Well, by definition, we have the commutator of A and B is equal to A, the left-hand operator applied to B, the right-hand operator, minus the right-hand operator applied to the left-hand operator. That's what we see here. So, knowing that order matters, let's go ahead and be careful. This A plus B is the left-hand side, so we have A plus B applied to the right-hand side, minus the right-hand side applied to the left-hand side. And here, just be careful with distributing, because we know that order matters. Here, the handedness of the distribution, we have to right distribute the Cn, so that's why we have AC and BC instead of just CA, so on. Here, we have the negative C that we need to left-hand distribute, so we have negative CA and negative CB. Be aware that all these things do come into, they do become effective and matter here. We're not just dealing with numbers, so the order matters. And if you've taken a linear algebra or abstract algebra class, you've seen this before, and you'll be ahead of the curve. So, just be mindful of the handedness, and then once you're there, you can kind of see that the colors allow for us to see the groupings that we need. We need a blue, purple, and purple, blue. We got that here. A, C, C, A, B, C, and C, B. We're good there. And the minus sign ensures that we get back to another commutator relation by definition. And we have the same thing here. So we just proved the linearity condition when we have the Q on the right-hand side of the bracket. All these things start to come back together, and that's why the author stated to start this chapter that the linear algebra background will start to make itself pop up. So if you need help with that or need more reinforcement, go check out the appendix, go check out any of the books online. There's plenty of resource, but definitely will help you if you know that so that you can understand what the quantum mechanics is trying to describe to you instead of learning the math. But onward we go. So then, if that's the case, we still need to prove the other distributive law or the product rule, whatever you want to call it. Different books have different things. Again, when we have this case, we see that we have the left-hand side and then the right-hand side. So apply the left-hand side to the right-hand side minus the right-hand side to the left-hand side. Okay, so we see that we just get our distribution as such. notice here that the ABC minus CAB doesn't give us much, but if we add in a convenient factor of 0 by the convenient factors of ACB plus ACB with the minus sign, then we can manipulate our way algebraically through convenient factors like this, and then we could refactor out later. Um, not too much, but what we want to do is to make this more convenient, we're going to move this bracket term into the middle here. So that's why we have this here. And what we see here is that we could left factor the A. Okay, again, we can do this because the handedness does matter. And then we could right factor the B, which we do here. That, again, going back to that orderness. And then we could see that we get back to our commutator definition, BC, and we prove that we have the we prove we have the distributive property here, and this kind of setup reminds me a lot of what I did in abstract algebra and linear algebra, of course. So just be aware that these algebras have these strict definitions, and we need to be careful with them. You can't just if you need a more physical example, you can't just add and multiply vectors the same way you do the scalar numbers, right? Vector addition, you have to break them into components. At the products, you have to think of dot product, vector product with the cross product. And so, these kind of identities look like what we saw in E and M as well because of that thing, because of that fact. Now, moving on to part B though, we see that we want to realize that in order to prove this commutator relation, we have to realize that these are operators. So we need something to operate on. And that's why we say let it act on a test function. Let it be whatever you want. Just make sure that you can highlight the certain properties that will become apparent shortly. All right, so in this first line, we have just the definition of, P getting plugged in, which is just the negative I h bar d by dx. We've seen that before. Really not too bad. Um, but now we just need to apply the bracket here, the commutator bracket. So the curly brackets, please don't confuse those for the Poisson bracket. I'm just trying to show that I'm keeping G on the outside of this thing for now. So, of course, left hand, right hand, minus right hand, left hand. Tidy this down. We see here that we have a negative I h bar in both of these terms. And of course, with that being said, we kind of had an intuition that we could factor it out, and of course, the linearity condition gives us that, and we kind of saw that again in property, or when we were in A or property 1, factor the constants out, no big deal. That being said, we still have to be able to now act on G in this bracket, so factor it out just to tidy it up. But these derivatives, the operators, have to act on what's to the right of it. That includes G. So here then, in this line 4, what we see is that we have, the derivative of just G, and then the derivative of the product of xn and G. And of course, if we have that, then we need to invoke the product rule. Okay? And calculus is nothing new to us at this point, but what I want to highlight is the fact that this product rule would not have been seen if it wasn't for this test function. So applying these test functions or setting things up like this is an algebraic trick to help us. Otherwise, these things would be hidden and we would not be able to do what we need to do in order to prove these statements. So that's why, be aware of these definitions and use them to your advantage. Otherwise, you'll be banging your head on a desk like I used to. But yeah, nonetheless, moving forward, we can simplify now. We get some pretty nice canceling going on here. You see that the derivatives with xn go bye-bye from the product rule. That cancels out nicely. Wonderful. That's exactly what we were hoping for. So here, of course, then all we're left with is this term in the middle. Has a negative sign. There's a negative sign out front. Goodbye. And so now we can tidy up the expression here. Recall though that we let this operating or the commutator bracket act on a function g of x. And we have a g of x in the result, so let's cancel them out, get rid of the test functions. We have thus successfully proved or shown what we needed to show out of this exercise. So similarly then, in part C, we just extend what we saw in part B. Instead of this x to the n, just put f of x in and run it through commutator bracket there, no big deal. We see, or excuse me, we see that once we have the commutator bracket, apply the product rule again, simplify down, you get the same result. Cancel out the test functions. At this point, nothing too crazy for you. So that was nice, quick, and easy. Nice to know for later, of course. But now we have Chapter 2 coming back in Part D with the harmonic oscillator. Let's just be very careful, of course, because these operators defined with the plus minus, that's going to need to be handled with care in the next part of this. So just be aware that the plus minus does read that if I have the top one, I'm plus minus plus, bottom I'm minus plus minus. So of course, easy to mess up on some of those things, but the Hamiltonian here was defined as such in Chapter 2. Let's see how we can simplify this bracket now. Cool, cool. Okay, so, linearity, we could factor out the h bar omega like we did the negative I, h bar, and b. No problem there. And then we, conveniently proved an identity in part A that we could, use linearity again with the commutator of a sum being the sum of commutators. And so we take the left-hand side, split it up, and that's why we have a plus minus in the middle of two commutators. We just simply applied what we proved in part A. Now note that the commutator with the scalar or a constant is 0. Okay, so here up in the top right, if I just have little a being a scalar, we see that that can move via the linearity through the operator, and so I'm just left with a b hat minus a b hat, which is 0. These kind of things come up all the time, so it's best just to make a list of these properties. Um, Again, just save yourself the headache. Make a list early. Okay, so moving on then. You see here that we're stuck, now that this cancels to 0, we're stuck with just this commutator, which conveniently we also proved in part A, expression 2, with the distributive law. So we have a product, a product of operators here. So split them up using part A, part 2. Okay, I'm just rambling at this point. So send it out. We see that we get this relationship here. Again, with the commutator of the A and the B term here, with reference to what we had in part A2, we see that these are operating on themselves, right? It's the same operator. So let's also note that in this property list, the same operator yields 0 as well. A hat, and the red and yellow, they're the same thing. So we end up with a squared operator. And so square minus square yields 0. That's just another convenient fact. So not only does this yield 0, it gets rid of this thing here. So we can finally boil down all our nitty-gritty stuff to this a hat out front with the plus minus and one commutator bracket. So we canceled the 1/2 out with the constants. We distributed out and canceled another part of that. Holy moly, what a question so far. Now, this is what I mean by we have to be careful with respect to these plus, minus, minus, plus signs. In the text, we were given that back in chapter 2, what was the commutator of a minus and a plus, which was 1. So that was given to us when we were defining and getting used to the ladder operators and defining the Hamiltonian with the ladder operators. Okay, but this only handles one case of what we have in the blue and green. This is only a minus plus and minus plus. How in the world am I supposed to get the other case where I have plus, minus, and which I don't have yet? Well, the answer to that is, well, let's use yet another property known as the antisymmetric property, where if I change the order of the operators in the commutator bracket, I just have to tag along a negative sign. Okay? And this should not come as a big surprise because, if we go back to the definition of the commutator bracket, we could just factor out a negative from both terms and get the same result. Also note, we've seen this kind of anti-symmetry argument before. Conjugates is a random example I keep coming up to, but also cross products. If we switch the order in a cross product, it's the same as putting a negative sign out front. So this anti-symmetry is definitely a thing. Be aware of it. Minus signs pop up at everywhere in these algebras, so be careful, please. But applying the ladder operator definition that we were given with the anti-symmetry property, we can find out what the other case is of plus minus as such. The opposite case, well, if we start with the definition that we had from the ladder operators, we know that that's equal to the negative of switching the operators around, so that gives us the plus here, the minus there that we need. Of course, if we just bring the line down, the left-hand side is 1, and we're still left with a negative on the bracket of interest. So push the negative over, and we get negative 1. So, finally, what we can conclude is that this bracket, or this commutator bracket here, if we go in order of plus minus plus, leads to a plus and a plus. So, plus minus plus leads to a plus. Minus plus minus leads to a minus, minus, plus minus, and then that leads to a minus. So this plus or minus 1 comes in pretty handy. And that's what we see is the result of what we were trying to prove. Messy is the way that I could best describe it. There's a ton of these properties. So, thank you for watching, and, we'll talk about more of these properties, and I'll just make a big list because I think that's helpful, much like the Dirac delta. But until next time, stay curious and happy learning.